Good evening, sir. Dr. D. Srinivasarao garu. I am Venkat Subbaiah, Chairman of State Center.
Good evening, sir. Good evening.
Sir.
Good
Good
evening.
evening, sir.
Yeah,
Professor
good evening, sir.
Venkateswar Reddy garu.
Good evening, sir. Good evening.
Good evening.
Engineer Brahma Reddy garu. Good evening. Satish Kumar garu. Professor Ramajacharya garu. Rayaswar Rao garu. Good evening to all of you.
Good evening. Good evening. Good evening.
Good evening, sir. Good evening.
Good evening, sir.
Sir, Mandala great.
Good evening. Good evening, Tom.
Very happy, sir.
Good evening.
Good evening, sir. Rayaswar Rao garu.
Good evening.
Convener and the chairman, I think it's time for us to start this event, sir. Good evening to one and all. Today we're going to have the Dr. NARLA TATA 24th Endowment Lecture, and the keynote speaker is Dr. D. Srinivas Rao garu. He is the Associate Professor at National Institute of Technology, Warangal. And the theme for today's endowment lecture is Role of Wideband Gap Semiconductor Devices in Modern Power Electronic Applications. I invite the chairman of the Institute of Engineers, G. Venkat Subbaiah garu, Dr. Venkat Subbaiah garu, and also the convener of the event, Dr. P. Satish Kumar garu. We also have the privilege of Dr. D. Srinivas Rao garu to be part of today's event, and we are lucky to have the son of NARLA TATA Rao garu, Gangadhar. Dr. Gangadhar garu is here, sir. And I also invite one and all who are part of this event, sir. We have Venkateswar Reddy garu, Dr. DJ Ramesh garu, in the past, immediate past, Chairman Brahma Reddy garu, Kella Navya garu, KVR Smurti garu, Adori garu, then Ramanjunachari garu, Rajeshwar Rao Manda garu, Venkatratnam garu, Vijay Gopal Parsuram garu, Y. Sai Krishna garu, Janavi garu. We also have with us the immediate past chairman, the chairman-elect, Professor Dr. Ramana Naik garu, and also have the keynote speaker, Dr. Srinivas Rao garu, Steven sir. Sir, I think we're going to have 5 minutes of time. I would appreciate each and every individual who are part of this event. Because 5 minutes, we have to go out and garland the great personality, Dr. NARLA TATA Rao garu portrait, and also we have to offer the flowers and light up the lamp. So I would appreciate everyone who would be viewing this event through the online, sir. And then we will come back and then we start the event, sir. Just give us 5 minutes. We'll have this event done. Garland the personality, great personality, NARLA TATA Rao garu, sir. Please.
Yes.
Picture coverage.
Johar, great engineer, Narada గారికి జోహార్ 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 నారాయణ గారికి జోహార్.
Right.
Sir, thank you very much, sir. Now I would request the chairman of Institution of Engineers, sir, to preside over the event and then conduct the proceedings, sir. Thank you. Thank you. Over to chairman.
Thank you, sir. Thank you, sir. Dr. K. Secretary, respected keynote speaker, Dr. D. Srinivasarao, National Institute of Technology, Warangal.
Good evening, madam.
Dr. K. Sitaram Babu, Honorary Secretary, Telangana State Center, Engineer B. Brahma Reddy, immediate past chairman, Professor Dr. Ramna Nayak, elect Dr. K. Satish Kumar, FIE, committee member, IEA Telangana State Center, and convener of the event, Dr. Gangadhar Garu, son of Dr. NARLA TATA RAO Garu, ENC, Dr. Ramakrishna Garu, FIE, Professor Venkateswara Reddy Garu, DJ Ramesh Garu, Kavya Garu, KVSR Murthy Garu, Meghana, Narasimha Garu, Professor Ramanujacharlu Garu, Mandava Rajeswarrao Garu, Ravikant, Satvika Reddy, Vijay Gopal, Karnagar Reddy Garu, our staff members of Telangana State Center, ladies and gentlemen, good evening to all of you. Today I feel it is a great privilege and honor to be with this August gathering and extend a warm and hearty welcome to the speaker and all of you for the Dr. NARLA TATA RAO 24th Endowment Lecture. I am glad to inform that the Telangana State Center of the Institution of Engineers India has been regularly organizing endowment lectures. They are totaling to 20 in the academic year. And the honor of eminent engineers like Engineer V. Subbarao, Engineer M. Tripathi Reddy, Professor K. Gopichand, Dr. J. Purushottam, Engineer G. Prabhakar, Engineer Koka Krishnamohan Rao, Engineer S. Balakrishna Reddy, Engineer G. V. Subbarao, Engineer T. Hanumanta Rao, Engineer A. P. Ranganath Swami, Dr. S. Raghavachari, Dr. NARLA TATA RAO Garu, whose endowment lecture presently we are organizing. Engineer Matur Gopal Rao, Engineer Gurram Kotreddy, Engineer Atturi Venkateswar Rao, Engineer R.L. Razu, Dr. John A. Murray, Dr. N.V. R.L.N. Rao, Engineers L. Venkatakrishna Iyer, K.V. Srinivas Rao, and M.L. Swami, Dr. A. Ramakrishna, and Engineer I. Basavarasu. I take this opportunity to say a few words about veteran Dr. NARLA TATA RAO Garu. Dr. NARLA TATA RAO, born on September 4th, 1917, completed his BSc in Electrical and Mechanical Engineering from the famous Benares Hindu University, Varanasi, and a diploma from the Jamshedpur Technological Institute of the Tata Iron and Steel Company, which is popular as a TISCO Limited, Jamshedpur. He then did his MS in the Power Systems Engineering from the Illinois Institute of Technology, Chicago, in USA. The Jawaharlal Nehru Technological University, JNTU, Hyderabad, later conferred on him the honorary degree of Doctor of Science. Dr. Rao served Madhya Pradesh Electricity Board from 1948 to 1972 in various capacities, right from divisional engineer to the vice chairman. Dr. Tata Rao built the Madhya Pradesh Electricity Board as an envious organization. He then worked as member during 1972-74 with the Central Water and Power Commission, Government of India. Dr. Rao has also been the president of the Central Board of Irrigation and Power, New Delhi, during 1976 to 79, and chairman of the National Council of Power Utilities during 1982 to 88. He also served the Andhra Pradesh State Electricity Board as its chairman during 1974 to 88. Dr. Tata Rao became synonymous to the energy sector in Andhra Pradesh. Dr. Tata Rao increased the installed capacity of the state grid fivefold by conceiving giant generation projects like Vijayawada Thermal Station, Nagarjuna Sagar, Srisailam, and Lower Soleru Hydel Power Plant projects. He formed a strong base for the state's electricity sector, which is now considered one of the best in the country. Dr. Rao was also chairman, Energy Research Committee of the Council of Scientific and Industrial Research, CSIR, New Delhi, chairman of the Expert Group on Development of Power Technology, Planning Commission, Government of India, member expert committee on the Enron project, Government of Maharashtra, and also as consultant to the Asian Development Bank, ADB, on the recognition of the Bangladesh Power Project Board. In 1992, he was appointed as advisor on power to the Honorable Chief Minister of Andhra Pradesh. Dr. Tata Rao won several awards at national and international levels and also brought laurels to the engineering profession and the motherland. Dr. Rao has been recipient of the Golden Jubilee Award of the CBIP New Delhi for the year 1978. President of India conferred on him Padma Shri in the year 1983. So it is a very prestigious award for him, and it is an honor for our engineers. He was also a recipient of Bharat Ratna, Sir M. Visvesvaraya Award, instituted by the Government of Andhra Pradesh and the Institution of Engineers India, AP State Center, in the year 1985, and the Om Prakash Basin Award in the year 1986. The IBPL Urja Research Foundation, Mumbai, selected Dr. Rao as the Energy Man of the Year for the year 1995. The Institution of Engineers India honored him with the Honorable Life Fellow of IEI in the year 1997 during the 12th Indian Engineering Congress held in Bangalore. Dr. Tata Rao always stood behind us in all our endeavors, such as World Engineering Congress, etc. Dr. Tata Rao always used to mention that the honorary life FOE conferred on him by IEI is higher than any other honor. So we have hats up for him for having affection for IEI. We revere engineering legendary of the era, Dr. NARLA TATA RAO, who made laudable contribution in the power sector and brought laurels to the engineering profession. So the tributes we can pay to Dr. NARLA TATA RAO is to emulate his qualities and follow his footsteps. Today, Telangana State Center arranged Dr. NARLA TATA RAO 24th Endowment Lecture on the topic Role of Wideband Gap Semiconductor Devices in Modern Power Electronic Applications by Dr. D. Srinivas Rao, Associate Professor, NIT Warangal. Since you all are anxiously awaiting to hear the talk from our eminent speaker, I am limiting myself and hope that you will really enjoy the talk. So on behalf of the Telangana State Center of IEI and on my own behalf, I once again extend a hearty welcome to keynote speaker, Dr. D. Srinivas Rao Garu, Associate Professor NIT Warangal, and all of you for this important event. Thanks to all. Now, before starting the actual lecture, now I request Dr. Gangadhar Garu to say a few words about the veteran engineer, Dr. NARLA TATA RAO Garu. Sir.
This has come as a surprise. I wasn't expecting to speak on this occasion.
I'm increasing your voice. Right, volume, right.
I'm extremely happy that the Institute of Engineers is continuing to hold the endowment lecture in honor of Father. It's something that I really appreciate a lot. And it's to the honor of Institute of Engineers. Besides Father, other preliminary engineers have been honored through this endowment lecture process. With this, I'd like to thank the Institute of Engineers for conducting this lecture. Thank you, sir.
Thank you very much, sir. Dr. Gangadhar Garu. Now I request Professor Satish Kumar Garu to introduce our keynote speaker, Dr. Srinivas Rao Garu.
Good evening, sir. Good evening, sir. Good evening, everyone. I'm very happy to introduce today's speaker, Dr. D. Srinivas Rao Garu. He was born in Andhra Pradesh, India. He received his BTech degree from Bapatla Engineering College in 2006. He received the MTech and PhD degree in Electrical Engineering from Indian Institute of Technology, Roorkee in 2008 and 2014, respectively. He is currently working as an associate professor with the National Institute of Technology, Warangal. His research interests include power quality, multi-level inverters, modulation techniques for multi-level inverters, development of new converter topologies, electric vehicles, and adjustable speed drives. He has published more than 20 research papers in various journals and presented more than 10 research papers in various international conferences. He has supervised 3 PhD scholars and guided around 50 graduate and undergraduate student projects. He has delivered more than 200 lectures in various conferences, workshops, and short-term courses. I'm very happy to introduce Dr. D. Srinivas Rao. Definitely, all the participants will enjoy, and they will get a lot of information and knowledge from his expert lecture. Thank you, sir. I request Dr. Srinivas Rao, sir, take over. Thank you, everyone. Thank you very much.
Thank you, sir. Am I audible to you, sir?
Yes, yes, audible.
Yes, sir. Okay, let me share my screen. I think my screen is visible, right, sir? My screen is visible, sir?
Yeah.
No, sir.
Is it
Screen
visible,
is
sir?
not yet shared.
Is it visible, sir, now?
Yeah.
Okay, okay.
Yeah, okay.
దాంట్లో పెట్టాలా ఆ స్క్రీన్ లో పెట్టాలా పెట్టు స్క్రీన్ పెట్టు సార్ మన పెట్టింది కదా ఇంచుకొని పంపుతారు అంటే
So, good evening, everyone. Today we will discuss
Good
some of
evening.
the advancements in the modern power semiconductor devices, especially aimed for the modern power electronic applications. Right. In this modern world, so this power electronics is the backbone for many technologies such as renewable energy systems, electric vehicles, high-speed trains, data centers, smart grid, and aerospace applications, and even space missions. So basically, these power semiconductor devices are the building blocks for the power electronic converters, So the converter may be a DC-DC converter or AC to DC converter or DC to AC converter, whatever. The basic building block is the semiconductor devices, right? If you look back in the history, basically the journey started with these power diodes and later thyristors, also known as silicon control rectifiers, and later moved to the BJTs as a switch and the power MOSFETs and IGBTs. And today we are entering into the era where wide bandgap semiconductor devices such as silicon carbide and the gallium nitride. So these devices are introduced, and each new generation has enabled higher efficiency, higher power density, and new applications. So where they were not possible earlier. So whatever the applications are not possible earlier, so by using the devices, so that realities that means that comes true, right? So you're aware that, right? All these semiconductor devices, so most of them are realized with silicon as a material, right? So any switching devices, some of the characteristics, so we need to identify. The first thing is the energy gap, and next we move to the electron velocity and the melting point, and followed by the thermal conductivity and the electric field. So these five are the essential parameters so that we look right. So for example, this energy gap and this electric field, so these are responsible for the high voltage operation of a particular switching device. So whereas this one, so velocity of the electron, so this is responsible for the high frequency operation. So these two together, thermal conductivity and the melting point, so that may goes to the high temperature application. So here, if you see, look into this, these are the silicon. So silicon is the innermost triangle, innermost thing here. So all these things are low. So whereas thermal conductivity, melting point, electron velocity, energy gap, and means electric field, so all are relatively low. So compared to the other devices such as silicon carbide and the gallium nitride. So this silicon carbide and gallium nitride combined it together, so we normally call as wide band gap devices. So here the band gap is usually high when compared to the other day. See, for example, this energy gap here. So if you see here, this energy gap is very small here for the silicon. So whereas for the silicon carbide and the gallium nitride, so it is much more higher, 3 times or more than 2 times higher than the silicon devices. So because of these reasons, so we can go for high voltage operation. So that is one reason. And another thing is that high switching frequency operation and high temperature operation. For example, silicon devices, maybe you can go up to 100 degrees centigrade, the junction temperature of the switch. By using the silicon carbide or gallium nitride devices, we can go up to 150 degrees or even 175 degrees also possible. So high switching frequency, if we talk about, so silicon based, so usually we go up to, if you are using IGBT, so we can go up to 100 kHz frequency. If it is a MOSFET, so maybe you can go up to 200 kHz frequency. So whereas if you are using a silicon carbide devices, you may go up to 1 MHz frequency, or if you are using a gallium nitride devices, you may go up to even 10 MHz frequency is also possible. So whereas come to this high voltage operation, so if you are choosing an IGBT or MOSFET, if you are choosing an IGBT, we have 6.6 kV devices are available in the market. And if you are using a MOSFET, so maybe at most we have 2 kilovolt MOSFETs are available in the market. So whereas if you opt for the silicon carbide, so in that we can go even up to 15 kV. So 15 kV devices are possible, whereas if it is gallium nitride, so this is usually relatively low. We have 1 kV devices or 1.2 kV devices are possible, right? So what is the main advantage by going with these wide band gap devices such as silicon carbide or gallium nitride is the high voltage operation is possible, high frequency operation and high temperature operation is possible. For example, if a high voltage operation is in that case, if you are using for HVDC applications like FACTS application or some any other applications, right? So you need to connect several devices in series to cater the required voltage. So if the devices are available with high voltage, the number of devices that connected in the series will be very much reduced. If the number of devices is reduced, the size will be reduced, the power density will increase, and also the reliability will be increased. And another thing is that high temperature operation, we can stretch the operation, or else we can allow some more losses in the device. For example, silicon devices maybe can withstand up to 100 watts. Maybe if you are using a silicon carbide devices, we can slightly increase their current rating so that they can withstand up to 150 watt or 200 watt power loss, or it can easily handle that much power loss. And another thing is that high switching frequency operation. So if we go for high switching frequency, so one of the main thing is that the size of the passive components, especially this size of inductor and the capacitors, so these two are normally used for voltage boosting or for filtering applications or filtering the waveforms. So these passive components like L and C, the size is very much reduced. For example, if the L is usually proportional to 1 by F and C is usually proportional to 1 by F squared. So meaning is that as you go for the high frequency, the size of these passive components, especially this inductor, capacitor, or it will be so very much reduced. Right. And also that leads to the size, if the size is reduced, that leads to the smaller footprint, and that leads to higher power density. So the point is that, so what exactly these wide bandgap semiconductor devices? So normally these semiconductor devices are classified based on their energy gap. So one means energy gap between the valence band and the conduction band. Silicon is having energy means wide band gap of 1.1 eV. So whereas for the silicon carbide, so it is around 3.2 times eV. So whereas for gallium nitride, it is 3.4 times eV. So what is the main advantage here is that, so it will increase the breakdown voltage, the faster switching speed, lower conduction and switching losses, and you can go for the higher temperature operation. So these are the benefits. So when you adopt these silicon carbide or the gallium nitride devices, so high temperature operation, so lower losses, faster switching speeds, and higher breakdown voltages. So whatever the drawbacks of the silicon devices are there, right? So those drawbacks can be easily overcome by using these wide band gap switching devices. Okay. So same thing. So what is the maximum, as of now, what are the maximum available ratings of these wide band gap devices? So this can be of different types. One is the silicon carbide MOSFETs, or this gallium nitride HEMT. So HEMT means high electron mobility transfer, HEMT devices. So you can see that the silicon MOSFETs are commercially available up to 600 volts to 15 kV devices are commercially available. And most common class is that, so 1.2 kV device or 3.3 kV device. So whereas we have some research prototypes, so where we can where it can withstand more than 30 kV devices also possible. So what is the advantage when you're increasing the number of when you're increasing the voltage level? For example, some applications you may require 11 kV, right? Some applications you may require 11 kV switching device, right? In that case, what we normally do, if we select some 3.3 kV device, right? So we usually connect 4 of such devices in to get this 11 kV voltage. So whereas if this 15 kV device is readily available, so one single switch is enough. Right, one single switch is enough for that. If one single switch is enough, so it will obviously, it will reduce the size, and it will also increase the reliability, right? So whereas this gallium nitride devices, so those are aimed for the low voltage and high frequency. There is some small difference here. The silicon carbide devices are aimed for the high voltage operation. So whereas these gallium nitride devices are aimed for the high frequency operation. So therefore, the silicon carbide devices used in the high power, medium voltage or high voltage applications. So whereas these gallium nitride devices are used in the low power, high frequency operations. Right. So these gallium nitride devices, so commercially available from the 60 volts to 700 volts. So common class is 650 volts, and we have devices so greater than this 3 kV are also demonstrated. Right. So coming to the applications, so this silicon, so if you see here, right? So this silicon corresponding to this silicon, so we have applications in the transmission lines, wind energy, or this PVs, electric vehicles, and some commercial elements. Right. So these are the high power applications. So wherever the high power applications are required, for example, HVDC effects or silicon devices are using, and we are replacing this silicon device with silicon carbide devices slowly, right? For example, for wind energy, earlier we used silicon devices. So now we are replacing with the silicon carbide devices, right? So whereas for the gallium nitride devices, so these are aimed at the low frequency or the high frequency, low powers, especially the power supply for the televisions, power supply for the washing machines, or power supply for the air conditions, mobile battery chargers, or data centers, or the other applications. So these are onboard chargers for the electric vehicles. So these are replacing with the gallium nitride devices. Right. The point is that, so these silicon devices, so where we used earlier for high voltage or high power applications, they are replacing with the silicon carbide devices. So whereas low power, low voltage applications such as television power supplies, data centers, air conditions, those are so now replacing with the gallium nitride devices. Earlier we used MOSFETs, silicon MOSFETs. So now we are replacing with the gallium nitride device. Understood. So if we come to the silicon carbide, so what is specialty of the silicon carbide? So silicon carbide means silicon is combined with the carbon atom. So this is we normally call it as polymorphism in the chemistry. So there are different structures are there. So one is the 3C-SiC, this is cubic SiC, and 4H-SiC and 6H-SiC. These three are the popularly used. So if we talk about this 3C-SiC, so this is ABC and the ABC. This is the 3C-SiC structure. So whereas 4HS, the H stands for the orthogonal, then C stands for the cubic. So this is ABCA, right? ABCB. This is the structure for the 4HSIC. So whereas for the 6HSIC, so this is lattice structure. So this is ABC, ABC, or ACB, like this. So out of all these, there are more than 200 polymorphisms for the silicon carbide are available. So these three are popular. And if you compare all these three, so this is the thing, right? So if you compare, this is 3C-SiC, it is a cubic structure, it is hexagonal, and this one is hexagonal. So this is the pattern that I have just shown. And this is the energy gap. This is 2.36, 3.26, and this is 3.06. And this is electron mobility here. And if you compare all these things, so what they found is that the 4HSIC is more popular, or in other words, it is merits are more, right? So therefore, this is used in the power MOSFETs and Schottky diodes. Whereas the 6HSIC, so this is normally used in the electronic circuits. So meaning is that, so this one, this 3C-SiC, so this is popular in the radio frequency applications and sensors and radiations for some applications, right? So here this is used in the radio frequency applications, and this is also used in the electronic or microwave applications, whereas this 4HSIC especially dominant in the power electronic applications like power MOSFETs or Schottky diodes. Right. So that means we are using 4HSIC structure for all our power electronic applications. Right. So if you compare this silicon and silicon carbide MOSFETs, so we have a higher breakdown voltage, so which means the voltage rating can be maintained. So which is means maintained. So still we are reducing the thickness of the device. So a wider band gap, so leading to the lower leakage current, and a relatively high temperature operation is also possible. So normally silicon devices, as we discussed, so we can go maximum up to 125 degrees. So whereas silicon carbide, we can even go up to 175 degrees as well. Right. So if you are using or if you are replacing the silicon with silicon carbide devices, so what are the merits we can get is that the first thing is the reduced switching losses. The switching losses will be reduced, and this will increase the efficiency of the overall converter. And another thing is the switching frequency. So that means we can have the smaller components or small filter sizes, inductor, capacitor, or also even high frequency transformer. The size will be very much reduced. So that will increase the power density of the converter. Normally power density are this much size. So what is the power it is handling in? It is cubic meter or cubic inch. So how much power? So that is present. So that is normally gives you the power density. Increased critical breakdown strength. So about 10x times more achievements than the silicon devices. So as we discuss higher temperature operations, so that means the cooling mechanisms or the heat sink requirement or other things will be reduced. So these are the merits, these are the advantages. So we will get, so we will replace the silicon devices with the silicon carbide device. So if you are aware some brief background about this power MOSFETs, you know that, right? One is the drain is there. It's a 3-terminal device. It's a gate, so gate pin, drain, and the source. The current will always flow from the drain to source. So there will be two types. One is the N-channel MOSFET and the P-channel MOSFET, right? So most of the times we prefer this N-channel MOSFETs because the mobility of the electron will be more compared to the P-channel. Right. So this is mobility of electronic side. So therefore we can go for the high switching frequencies. So whereas mobility of these holes is low, so we can go for the low switching frequency. So thing is that, so we normally prefer N-channel MOSFET. And in case of MOSFET, there are two things are there. One is the depletion MOSFET. So we normally call it D MOSFET. So whereas this MOSFET, E MOSFET or E mode, right? This is E mode or this is D mode. Right. So these are some basic differences are there, or D MOSFET or E MOSFET as we discussed, right? So this depletion MOSFETs are normally on, right? So normally on. So whereas this is E MOSFETs are normally off. So here we need to give some negative voltage to turn off the device. So here, so we need to give the positive voltage to turn on the device. So there are some differences are there. So most of the times we will prefer this E MOSFET. So we normally prefer N-channel E MOSFET. N-channel enhancement MOSFET or N-channel E mode MOSFET. Okay. And there are as we similar to the MOSFET or silicon based MOSFET. So here also this is the equivalent circuit of a silicon carbide MOSFET. It consists of some parasitic capacitances between the gate and drain, gate and source, also between the drain and source. So these are not linear capacitors, or these are depends on the temp at what voltage you are operating. And this is the stray inductances, and this is the gate pin resistance, and this is the source pin resistance. This is stray inductance of the source channel, and these are the gate resistances and the gate gate path stray inductance. So this is the gate terminals. This equivalent circuit similar to a silicon based MOSFET. So this power loss calculations, so this is also similar to a MOSFET. So now what exactly inside this MOSFET or any MOSFET or silicon carbide based MOSFET or anything, right? So first thing, this MOSFET looks like this, right? So these pins were one gate pin, drain pin, source pins, or anything, right? So if you open this one, you can see some threads, something like this, right? Some parallel paths, so which is connected to the source pin. So here, one important thing is that, so when any device, any power electronic device, when it is failed, right? So when it's disturbed or when it's disrupted, right? In that case, there are two things are possible. One is the open circuit, and another thing is short circuit. In some applications, so we need to short circuit the device when it is failed. For example, your connected series connected devices are there. So 3 series connected MOSFETs are there, right? And these 3 are withstanding some voltage. For example, this device is failed. If it is open circuit, right? What happens is that, so this entire device will be useless. All right. So what you are supposed to do is that, so we have failure mechanism such a way that it should be short circuit. And moreover, now we have only 2 devices are there, and those 2 devices are supposed to withstand the voltage. So therefore, we normally connect a few more switching devices as a redundant. If one device is failed, so the burden should not be shared among the other devices, right? So that means if we are not properly maintained, right, in that case the other devices may be failed. So therefore we normally connect some extra devices for the safer operation. So in case of series connected devices, we expect that the failure mechanism must be short circuit. Or else in case if you are using a single device or something, right, we normally expect that the failure mechanism should be open circuit. So based on that, there are two types of MOSFETs are there. One is the wire bond and another one is the press pack. So in case of wire bonds, so this is wire bonds, some of the wires will be there. For example, if it is failure, right? So this connection is lost. So there will be no connection here. So that means the device will be open circuited. Right. So this is about the wire bonds. So whereas another thing is the press pack IGBTs. So this is especially used in the applications, high voltage applications, HVDC, FACTS, or some other applications where you require high voltage or where it can withstand high voltage or number of devices connected in series parallel. In that case, they prefer this press pack MOSFETs or IGBTs. Right? We have some small springs will be there inside the device. So these disc springs will be, so whenever it is failed, right? So these springs are attached together and by using this gel and other things, right? So in that case, the current will be bypassed here and it will be acts or this current will be bypassed here and it will act as a short circuit. Understood? We have wire bond and press pack. So in case of wire bond, it is open circuit. In case of press pack, it will be short circuit. Okay. And another thing is packaging of this semiconductor device. So this is one of the innovation here. So we have normally all the semiconductor devices are comes in different manner. One is the discrete devices, one is discrete form like this individual devices. All right. So these are discrete devices, and another one is the packages. Package means, for example, this entire thing, for example, it is marked here, right? So this is one phase leg. So whereas this device is there, right? So this entire thing is one three-phase inverter. So this entire thing, this is A phase leg, B phase leg, this is A phase leg, B phase leg, and the C phase leg. This is A phase leg, B phase leg, and C phase leg. This entire thing is the one inverter. So these are the connections for the DC link, and this is A phase, B phase, C phase, and this is the firing signal for A phase. This is firing signal for the A phase devices, B phase devices, and the C phase devices. So whereas this one is one phase leg. So these are known as packages. Right. So these are discrete devices and these are packages. So whereas other things as well, so which is known as bare die. So there is no package, nothing. So just simple a silicon or silicon carbide wafer. So this is known as the bare die packages. So we have discrete packages are there. Some modules are there. All right. So discrete devices, modules. These are called as modules and bare die devices. Okay. So if you talk about the discrete, so we have some TO, it is transistor outline. So normally some hole will be there. So this is a through hole devices. So we have some hole will be there. So from this hole, we normally connect to the heatsink. So these are surface mount devices. So we will connect these devices to the surface of the PCB. All right. So there is another thing is that this is TOLL. So this is a transistor outline. LL means leadless. There is no contact points here. These are some leads are here, right? There is no contact points. There is no leads here. Okay. And there is another innovation here. Normally, all these MOSFETs or IGBTs are 3 terminals, right? So we sometimes have some extra terminals. All right, you can see this is a 4-terminal device. This is also 4-terminal device, whereas here some lot of terminals are there, right? So this is usually a 7-terminal device. Actually, we have the gate pin, source pin, and the drain pin, or the gate pin, collector pin, and the emitter pin in case of IGBT. But we have some redundant pins are there. For example, the source pin is redundant. So some extra source pin is present. Similarly, some 6 source pins are collectively present. So here, in case if you are using some high voltage applications, right? If these two pins are near, right? So that means the creepage or the clearance distance, or we need to maintain some gap between the devices, right? So if you have provide this one, the gap between the device will be slightly increased. So that is one advantage. All right. So there are other advantages as well. For example, if you see here, these are so this is a 4-pin structure, right? So we have drain pin. So for example, this pin 1, so this is the drain pin, and this is source pin. So this one is the source pin, and there is another pin for this. So this is known as Kelvin source. So this is Kelvin source, and this is gate. You are aware that, right? So generally we will apply firing pulse between these two terminals. So between the source and the gate terminals, we will apply the firing pulse. But here, what is interesting thing here is that, so here we use this additional pin, this Kelvin sense pin or Kelvin source. These two are same only. These two pins are same only, but instead of these, so we will use these pins for the gate signal. So this source pin is used for the power conduction, so whereas this is used for the low voltage gate driving. Understood. So what is the advantage when you're doing this one, so that you can understand from here. So this is the 3-pin device, right? This is 3-pin device. So whereas this one is a 4-pin device or 4 layer, right? So here there is just some parasitic inductances and all. So these parasitic inductances, so that will slow down the switching operation, right? See here, this is how this parasitic inductances of this PCB, you can see here, this is a 4-pin structure. So here, instead of connecting here, we are using a common source pin, right? So here we are using a Kelvin source here, this is gate pulse, and this is the source pin. So whereas here, so this is gate pin, source pin, right? So this is gate pin, this is source pin, and this is the drain, right? So here we have some Kelvin source pin. So between these two, the gate pulse is connected, and we will bypassing this stray inductance, which is caused by the PCB layout or some device inside things, right? So we are using dedicatedly this for the power current conduction. So we are using this dedicatedly for the gate driving. So by using so it will increase the speed of operation. So that means we have faster on and off times. So if you have faster on and times, right, this is the significance of this one, right? If this is taking some own time, right? So this is also taking own time. So because of this, you have the power loss like this. For example, this is taking faster time. For example, this is reducer like this. So this is also reducer like this. So what happens is that, so this will be like this, right? So these transitions, for example, if it is faster, it is faster, this is also happening faster, right? So that will reduce the power loss. So because of this additional, just we are not done anything, right? Just we have one more pin. So because of this pin, the power losses is very much reduced. So how much it is reduced? So this is the 3-pin structure. All right. So this is 4-pin structure, and this is a 7-pin structure. Right. See, you can see here, this power loss in single device is more than, this is around 425 or 430. You can see this power loss is just 100 watt only. So whereas here the power loss is even less, it is 80 watt or something. Right. So this is one of the innovation, especially in reducing the power loss. In other words, it is increasing the efficiency. This kind of these kind of devices, especially used in these electric vehicles or this grid integration of PV and other. So where the efficiency is very much important. For example, electric vehicles, even if you are even you are saving 1% or 2%, right? So that will increase the range of the vehicle. Okay. So come to this bare die packages. So as we discussed, so just silicon vapor is used. All right. So with this, we can directly go to the temperature up to 175 degrees. Right. There is no oxide, there is no gate, nothing is there, right? So no oxidation forming, or the means this will be right. And also they can withstand from short circuits also, and they have a reverse current supply is also possible. And with this, you can also go for the high frequency, power density will be increased, the ruggedness also increased, right? And also we have some improved cooling. So everything is open, right? So we have some improved cooling. So this is bare die. So normally in applications, especially space applications or some applications of some military grade applications where they normally use these bare die packages in some concealed environment. Right. Sometimes we need to operate these MOSFETs in parallel or some series, right? For example, you are considering some automobile applications. Let us assume that so automobile batteries normally come with 400 volts battery, or sometimes if it is a 800 volt battery, right? For example, in case if you consider some motor rating is around 200 kilowatt motor, you consider, right? So what is the corresponding current rating? So that is around 500 amperes. So here you require a 400 volts and you require a 500 ampere switch. So this 500 ampere switch may not be available, right? So if your 100 ampere switch is available, right? So we normally connect five or 600 ampere switches in parallel. All right. So five switches or six switches, or normally five switches are connected in parallel so that you will get the required amount of current. Right. So this how it will be this 5 amperes, right? So all these 5 amperes are simultaneously conducted. The on time supposed to be same. For example, five devices are this is five devices here connected, right? For example, this is 1, 2, 3, 4, 5 devices are connected in parallel. All are supposed to are expected to carry this 100 amperes of current. If, for example, this starts early, right? If this switched on early, what happens there? This device will be damaged. All the current will flow through particular device, right? So therefore, we normally have some equalizing circuits. So also we have some other things. For example, if you are operating in parallel, so you must ensure that so if two devices are there, so we follow this kind of structure. If three are there, we'll follow this kind of structure. If nine are there, you'll follow this. If six are there, like this. So we need to symmetrically arrange these so that dynamically and steady state both conditions we are supposed to equalize. All right. So that's why this is one of the main drawback. That's why all the automobiles nowadays are they're going for the 800 volts battery. So advantage for the same machine, right? If it's 100 kilowatt ampere, now the current rating is only 250 amperes. So now no need to go for this 500, 100 amperes, five switches in parallel, right? Maybe if it is 250 amperes, the 200 amperes are, if you, that devices are readily available. So now one single switch is sufficient, or else if you choose 100 ampere switch, you just need only three switches. All right. If you're choosing only 100 ampere switch, right? So that can simply carry the 300 amperes. Or if you 250 amperes, one single switch is there, so that single switch is sufficient. All right. So this is one of the advantage. So when you go for high voltage batteries, right, the current will be reduced, and one more reduce, as you know that, right? The current reduces, right? The I square R losses will be also reduces, and also the voltage is more. The power transfer capability is also more. We know that, right? V1 V2 by X into sine delta. So if this is the power transfer, right? As you are increasing this voltage, the power transfer capability also increases, and that leads to the battery charging. So that can be done with 350 kilowatt charger, or even 500 kilowatt charger also you can use to charge this 800 volts. Whereas if it is 400 volt architecture, it is mostly limited to 150 kilowatt charger. So this will take usually 45 minutes or 45 minutes or so for charging time. Whereas if you use for 350 kilowatt, so maybe you can charge up to 25 minutes or 30 minutes, less than 30 minutes, right? So come to this gallium nitride devices. So as we discussed, so these are used for the low voltage, high frequency applications. Low voltage, high frequency applications. So compared to this silicon based or silicon carbide, so we can compare. So we can have 115 kV devices are there. So these for low voltage devices, right? So electron mobility are also higher in case of these gallium nitride devices. Thermal conductivity is more or less same in both cases. So switching fields, so this gallium nitride used for ultra high frequency applications where you can go up to 10 megahertz frequencies, right? So we can go up to 10 megahertz frequencies. So as we discussed, so this silicon carbide used in the silicon, so this gallium nitride is used in the low voltage, high frequency applications. Frequency operation, so lead to soft switching performance. So there is no reverse recovery current. The operation is faster. And one important thing is that, so normally for any device, silicon device, or normally we require 15 volts or to 20 volts. So where to turn on the device. So whereas for this one, so just 5 volts is sufficient. Correct. And one more, just 0 to 5 volts is sufficient. And they can go even up to means you can efficiency up to greater than 99%. And one more thing is that, so they're inherently bidirectional. For example, in case of inverters, right, we normally connect one freewheeling diode or feedback diode, right? In case we are using some silicon means MOSFET or IGBT. So whereas gallium nitride devices, they're symmetric device, they're inherently bidirectional. So no diode, nothing is required. As you are changing the firing pulse, as you are changing the current direction, so automatically the channel will conduct in the opposite direction. Right. So this is what we did. This is bidirectional power flow is naturally it is a bidirectional power flow. Right. So there is no parasitic body diode is required. The channel itself is symmetric, so the electron can flow both directions. So once the device is on. Okay. So once the device is on, the electrons will be flow both directions. So generally, any devices can be of a planar type device or the vertical type devices. Planar type devices mean, for example, this is source pin and the drain pin, right? The current will flow from the drain to source like this. This is planar structure. Some structures will be something like this, right? So current flow is from the top to bottom. So this is normally known as vertical structure. So this is usually a planar structure. And moreover, the structure is symmetrical here. The structure is symmetrical. Illuminated devices, especially in the charger for industrial vehicles, electric vehicles, or charging stations, uninterruptible power supplies, servo motors, and the telecom applications, data centers, and PV inverters, or also some applications in the electric vehicle, onboard chargers, and DC-DC converter inside the vehicle, and also we use it for the traction inverter applications. These are some of the notable applications for the gallium nitride device. So normally these applications are found less than the 10 kilowatt range. So wherever some 10 kilowatt or less than 10 kilowatt or 11 kilowatt there, so they have dominant applications here using these gallium nitride devices. So these applications, especially in the PV inverters, are also applications in the data centers, uninterruptible power supplies, and also applications related to onboard chargers for electric vehicles, right? Applications related to the our mobile battery chargers, right? Our mobile battery chargers. For example, if you remember 10 years or 15 years, so we had just only 5-watt charger is available. Only 5-watt charger. So that means if your battery voltage is 5 volts, it can carry the current up to 1 amperes. And typically, a 1500 milliampere hour battery, that small size battery, it will usually take 2 to 3 hours to completely charge that battery. Earlier. So later what happens is that we have 10-watt batteries are there. So we have the current instead of 5 volts. So after that the current is increased to 2 amperes. So that will slightly cut down the time. Alright. So now we have 20-watt chargers are there. Even now if you are using some Realme phone or some OnePlus phone, we have 70 or 150-watt charger or 100-watt chargers are there. So typically it will take around 30 minutes, less than 30 minutes to fully charge the device. Capacity earlier is 1200 milliampere hour or 1500 milliampere hour. So now almost all mobile phones will comes with at least 3000 milliampere hour rating. So now we have even 240-watt chargers are also available, right? So 240-watt chargers are also available with these gallium nitride devices. So typically this charge is 5000 milliampere device or battery in less than 10 minutes, right? Even less than 10 minutes. So these kind of chargers are commercial now available. For example, if you buy some Realme phone or something, right? So they come with this 240-watt chargers, so which is normally known as PD, USB ESP, PD, power delivery, and we have some namings are there like type C, 3.1 PD connection, right? Type C 3.1 PD connection. PD means power delivery. Even nowadays, now even that mobile means even for laptops also they're not giving any charger, right? So the same charger we can use it for so many applications like this 240 charges. Even the laptops can also charge using this 240-watt chargers. So this charging use, for example, this 240-watt charging, right? This charging can be done at very high voltage, for example, 48 volts, 5 ampere current. Like, so this will simultaneously charge the battery of the mobile device, and as well it will charge the battery of even for the laptops or so many handheld devices. And inside that, so they normally use these gallium nitride devices and they will operate extremely fast. For example, this 240-watt charger, right, they operate at 2 megahertz frequency. So that means the switching speed is too high. So this switching speed is too high, right? Extremely high or ultra fast. So therefore that will potentially reduce the size of inductor and the capacitors and filter. That will size will be same only. This 240-watt charger or even this 5-watt charger, the size is more or less same only. So you can see how much the power density is increased. And also this is even operated more than 98% efficiency. So whereas earlier the efficiency is very poor, not more than 60%. Right. So as we discussed, if you want to drive a, so we'll come back to this. Right. We will discuss some of the applications related to this wide bandgap device. So one of the commonly used or one of the application is the replacement of this transformer with a solid state transformer. Right, replacement of these existing transform or pop transformers there, right? Especially these distribution transformers. So nowadays they are replacing with solid state transformer. Solid state transformer means basically it will build with the semiconductor devices, right? So inside that, so instead of using a 50H transformer, 50H transformer, we have high frequency transformer will be there. For example, it is starting from this is 11 kV or 13.8 kV in other countries at 60H or 50H. So this AC supply, so first will convert into DC. Right. So by using this front end converter, we convert this into DC. So next we have another DC-DC converter. Right. So this will operate high frequency. Here, so we have high frequency transformer. High frequency transformer. So you're aware that, right, transformer, when you're increasing the frequency, the size of the core will be very much reduced. For example, for size comparison, if you have this is the size of a 50H transformer, right, 50H or 60H transformer. If you opt for 20 kHz transformer, the size will be this much only, very much small. This is corresponding to 20 kHz transformer. Almost 95% of the size will be reduced if you go for a high frequency operation. Right. So this is high frequency transformer. So where you have DC to DC transformation is done. Again, your DC supply at different levels, right? Based on your requirement, you can connect one inverter at one voltage level and another voltage level, another voltage level. So here you have, so typically 440 volts. So if you assume this is 11 kV transformer, and here you have 400 or 440 volts, you are on the other side. Right. So one of the main advantages of these switching devices and all, right? So normally transformers, so one of the basic drawback with the transformer is the low one thing is that low voltage, right? For example, if the load is increased, right? Low voltage, reactive power burden, and also it consists of some harmonics. All these will be there, right? So whatever the drawbacks there, right? All these drawbacks can be overcome. Still, it will draw the, if you control properly, right, still it will draw the sinusoidal current from the source, no harmonics, no reactive power, nothing, right? And also on the secondary side, so we can regulate the voltage. So even if you're increasing the load, so still we can regulate the load. So there are some drawbacks as well, right? So these are not rugged as the conventional transformers because these switching devices are there, right? They normally will not withstand. For example, if you design some motor, right? So normally, if you, even though it is rated for 16 amperes, you can usually go up to 25 amperes also. We can go for some short duration of time. So whereas for switching devices, if it's 16 amperes means, so we need to strictly follow the 16 amperes. Even if you run for 1 minute or 2 minutes, the device will be completely failed. So whereas for these conventional transformers or motors, right? So it can withstand means overloads for a more durations. Right. This is one application. So another applications, as we discussed, this is 240-volt or dual port charges. Dual port means you have two outputs are there. So that means you can simultaneously charge the two mobiles, or you can charge your mobile as well as your laptop. So see, here also you have input here. This is based on the gallium nitride device. So this is this symbol for a gallium nitride. So here this is input stage. You have power supply here, and here this AC is connected to DC here, and again you have one DC-DC converter here, normally known as the dual active bridge converter. All right. So on the other side, say you have one more buck stage will be there. So we'll reduce the voltage here. So we can two ports are there. This is one port and this is another port. So this can withstand up to 240 watts, and this is also capable to work at the 240 volts. So here all these things are the gallium nitride device except these two devices. Right? These are silicon carbide device. So this is known as the totem pole circuit, or this one, for example, this A phase, right? This is A phase. This is known as interleaved converters. So because, so the current will be shared here. So whereas the full current will flow here. So that's why they selected the silicon carbide device. Right. So here you have the high frequency transformer here. You have high frequency transformer here. So you can see here, right? This is the high frequency transformer inside this diagram. You can see this high frequency transformer, and these are the gallium nitride devices here, and these are the silicon carbide devices here, and also you can see the buck stage. This is the buck converter, right? So this is this stage here, right? So this is the inductor, so boost inductor. So this inductor LB here, right? You can see here. This is the input stage, this is input stage, and we have the output stage on the other side. Okay. So one more application is the onboard charger for electric vehicle. So one more application is the onboard charger of this electric vehicle. So this can capable of powers up to 11 kilowatt. Right. So you know that, right? Two types of charger is there in the electric vehicle. One is onboard charger. So normally we'll feed with AC supply or the single phase AC or three phase AC. So whereas outboard charger, so that we normally charge your vehicle at the charging stations. That is usually DC charging. So this input, so maybe a three phase voltage. And after that we have this AC to DC conversion, so which is known as the power factor correction and other stages. And one more thing is that this is power factor is also unity, and still it will draw the sinusoidal current. Right. And this is the DC-DC stage here. So the number of stages are there. For example, this is one DC stage 1, 3. There are 4 DC-DC stages are there. All these all our outputs are connected in series. All outputs are connected in series, so that you will get, usually you will normally get 400 volts or 800 volts depending on the which battery are used. Right. You can see here, these are the switching devices here. All these are the switching devices, and these are the corresponding, these are high frequency transformers, and these are high frequency transformers, and these are the corresponding inductors. Right. So this is based on the gallium nitride devices. Right. So one more application is the EV drivetrain. So that is the main motor, so where we connected. So you can see this is based on the silicon carbide devices. Normally drivetrain is 240 watt or even 100. It's usually more than 100 watt or 200, 300 kilowatt motors we normally use, right? So this is another type. This is T-type converter. So this is a 3-level inverter. So we have this. These are realized with the silicon carbide MOSFET, and this is the inverters. So where these are used to drive the motor of the EV. Right. So motor of the EV. This comes from the DC link. So before that you have the batteries connected here. You can see these are the switching devices here, right? So corresponding these inductors here somewhere here, these are the coupling inductors here. So all these things you can see here. Right. So what we understood is that as we are increasing, right, as we discussed, right, whatever the possibilities are, for example, no one is observed, right? So achieving charging your mobile device is less than 5 minutes or 10 minutes is it's an engineering task, right? And also replacing the solid state transformers with these switching devices is a remarkable choice. For example, this DC link voltage itself is around 22 kV, right? So if you are using some normal silicon based devices, you need to connect at least 10 devices or 5 devices, 6 devices are in series. So therefore, if you opt for 15 kV device, only 2 devices are sufficient. So only 2 devices in series is sufficient. Right. So whatever the things that are not possible or things that is there, right? So we are increasing that. So one aspect is that we are increasing their efficiency, or we are increasing their power density. And as we discussed, right? So whatever things which are not possible before, or now we are making it possible. Right. So this is about the lecture. Uh, Right. So this is about the advancements in the switching devices, especially these wide band gap devices in the modern power electronic devices. If you have any doubts or anything, so please let me know. Have any questions?
Yes, sir. No questions are there. Okay, sir. Sir, thank you very much, sir. You have
Yeah,
given
thank you.
very interesting lecture, sir. So all advanced topics you have told for us today, and we have enriched the knowledge of all the participants towards the modern micro, that is electronics, sir. So you have covered the important topics like 5 essential parameters of semiconductors, such as melting point, electron velocity, energy gap, electric field, and thermal conductivity. And they also enlightened about us what is wide band gap semiconductor and the applications of silicon devices, then how the silicon devices are replaced by silicon carbide, and the different types of silicon carbide such as 3C-SiC, 4H-SiC, 6H-SiC, and their applications. And we have touched upon many advanced topics, sir. So thank you very much for your great lecture, sir.
Yeah. Thank you, sir. Thank you for
And
giving the
I'm
opportunity.
also proud to say that a product of NIT Warangal, sir. I completed my
Oh,
BTech
nice.
in mechanical engineering in the year
Oh,
94.
okay, okay. Nice, sir. Very nice. Nice to meet you.
Thank you, sir. So now I request
Sir,
Dr. K.C.
can I join one question?
Yeah, sure, sir. Sure,
Sir.
sure.
Okay, sir.
Yeah, Dr. D. Srinivasarao garu, namaste. I am
Yeah.
Brahma Reddy, immediate past chairman. Before the present chairman, I was the chairman of this institution of business. I have a small question, sir. Kindly clarify. Sir, actually, you have nicely explained about the semiconductor and devices. But I have one question, sir. Whether like in terms of conduction losses and other application part of it, what are the major difference between power MOSFET and IGBT, sir?
Yeah. So normally, that all depends on generally power MOSFETs, right? If it is silicon based,
Yeah.
right? If it is silicon based one, the power losses are more in case of MOSFETs. So that's why we are operated for the limited voltage. Generally, if you are before inventing the silicon carbide devices, so normally, so the silicon based MOSFETs are used for the low voltage applications, not more than 600 volts. All these DC-DC converters, they use these MOSFETs. So whereas for inverters, whereas for grid level inverters or HVDC and other, so they normally prefer the IGBTs, right? So generally efficiency point of view, so both will be more or less same only. But generally, if you go for the high voltage operation in case of MOSFETs, their efficiency will be usually poor. So now what
But
happens is that wherever we are using IGBTs, right? So now they are replacing with the silicon carbide based MOSFETs. So wherever earlier used the silicon based MOSFET, right? So now we are replacing with the gallium nitride devices. Right. Yes, sir.
sir, but then how the N channel is being fabricated in IGBT? Like
N-channel?
MOSFET, say N channel and P channel is made by mixing the silicon with the either phosphorus or interacting with the boron
Yeah.
or all the materials.
Yes, sir.
But in IGBT, this bipolar insulated gate bipolar transistors, how that happens, sir?
This is also same thing, sir. More or less same thing only. Both are same
The
thing.
same
There are
material
different
is
layers.
used, or no, you are saying the low power this one, and the other one is a little bit higher.
Yeah.
Then how what material is mixed? Like same phosphorus and boron to get N channel here and P channel, or other some other material is used?
As far as I know, same material is used, sir. Only in case of IGBTs, there are some additional layers are there, like buffer layer or some additional layers they normally keep with different types of means different levels of what we say doping. Okay. So the materials are more or less same only, except in case of MOSFET, right? They normally coated with the silicon dioxide layer, right? So remaining things are more or less same only, sir.
Thank you, sir. Thank you.
హలో డాక్టర్ శ్రీనివాసరావు.
Yes, sir.
నమస్కారం అండి.
Namaste.
My name is DJ Ramesh. I am chairman of Vijay Electricals, Hyderabad.
Oh, nice, sir.
Nowadays, solid state transformers are taking a front stage in the world data center power.
Yes, sir. Yes, sir. Yes.
I would be interested in going for research and development program on this subject. Would you be able to help me?
Sure, sir. Definitely, sir. I am working in this area from past 5-6 years.
Are you working for any company or only with institutions like?
No, individual research only, sir. Individual research only. Okay. We developed some of the.
Basically, I mean, the whole of America, for all their data centers, they are looking to, providing power supplies with SSTs.
Yes, sir. Yes, correct. That is true.
And I'll spend some time with you, and my wish is that we can associate each other to develop this product.
Sure, sir. Definitely. Okay.
My phone number cheptara?
Yeah, sir. I will tell you, sir. 7842.
Yeah. 7842-001-002.
Yeah, correct, sir.
Okay, and I will be in touch with you.
Sure, sir.
When is the right time for you? For me to talk to you.
Oh, you can call anytime, sir. No problem. Okay. Anytime in the afternoon, you can call.
Once this is over, I will be in touch with you. Okay, thank you.
Yeah, thank you, sir.
Okay, sir. Now I request Dr. K. Sitaram Babu to propose vote of thanks.
Sir, thank you very much, sir. Dr. Srinivas Rao Garu, Dr. D. Srinivas Rao, Associate Professor at National Institute of Technology, Warangal, sir. It's a wonderful lecture, sir. And I also thank the chairman of the Institute of Engineers, G. Venkateswaraya Garu, and the committee member and the convener of the event, Dr. P. Satish Kumar Garu, for having made this event reality, sir. It's a wonderful lecture, sir. And we also acknowledge some of the members and the fellow life members and associate members who have joined as part of this event, sir. Dr. Mari Ramesh Garu, Secretary-elect, Institute of Engineers, DJ Ramesh Garu, Satvika Reddy Garu, Navya Garu, Rajeshwar Rao Mandwa Garu, KVRS Murthy Garu, Ravikant Garu, Krishnaya Garu, N. Narsimha Garu, Ramakrishna Garu, Karnakar Reddy Garu, Janavi Garu, Ujjwala Garu, Anusha Garu. And we also acknowledge the presence of Rama Garu. Now she's the honorary joint secretary and committee member for the Institute of Engineering, Telangana State Center, and Shyam Prasad Reddy Garu, council member, sir. And with this, sir, we wind up today's program, but I appreciate everyone to stand up for the national anthem, sir. And you want to, his son is here, sir. You want to say anything, please go ahead, sir.
I'd just like to go.
भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे.
Sir, there is just 1 minute, sir. Son of NARLA TATA RAO Garu, Gangadhar has to say just, in couple of sentences, sir, please.
I would like to thank Dr. T. Srinivas Rao Garu for the excellent lecture he gave. I hope his talent will be used by the industry to increase the power electronics capability of our country. Thank you very much, Dr. Srinivas Rao Garu, for giving this wonderful lecture in honor of Father. Thank you, sir.
Yeah, thank you, sir. Thank you for giving this opportunity to me.
Thank you very much, sir. Now we'll wind up the event, sir. Thank you. Thank you to one and all.
Thank you.